This is the last section in chapter 12, 3D vectors, which is applications to mechanics. Very straightforward. Most of this work you've done before in the applied year 1 or year 2. Basically, you can, before we had forces as vectors, we had velocity as vectors, we had acceleration as vectors. So a force can be a vector, velocity can be a vector, acceleration can be a vector. And basically, if you're finding the sum of forces, you just find the sum of the vectors. Sum of vectors will give you the resultant force equals resultant force. If you've got the velocity, if you do Pythagoras on that, you'll get the speed. You can also stick these in Suvat formulas. And the acceleration, that can be just put into any Suvat formula, but you're going to have a vector there in your equation. Obviously, the only thing that can't be a vector is time, but that's not a problem. So any one of your Suvat equations, you can put that in. And if you have 2 points, A to B, and you work out, if you do Pythagoras on those, you'll get the distance between those 2 points. Okay, so most of the groundwork you've done is just another number. So example 13 on page 347. What you've got here, we've got a mass of a particle. That can't be a vector. It's going to be a scalar, 0.5 kg. And we've got these 3 forces, F1, which is, I'm going to write it as a column, just for ease. 2, minus 1, 2. F2 as a column, minus 1, 3, minus 3 or negative 3. And F3, 4, negative 3, negative 2. They want us to find a resultant force in part A. Well, that's just going to be F1 plus F2 plus F3. So if you add those together, I think I've written a 2 down there. So 2 minus 1, which is 1, plus 4 is 5. Then I've got negative 1 plus 3, which is 2. Take away 3, which is back to negative 1 again. And then the last one I've got 2. 2 minus 3, which is negative 1, minus 2 is negative 3. Okay, so there's my resultant force. So all we've got to do is just add them together. That's very straightforward. So you can write that in a column, you can write it, what is Newton's there, you can write it in I, J and K. Normally when we're dealing with mechanics, we use I, J and K notation. Find the acceleration of the particle in that form. So in part B, we can just use F equals ma. So we have a resultant force 5 minus 1 minus 3 equals 0.5 times this acceleration, which is a vector. So if we basically times both sides by 2, we'll get 10, negative 2, negative 6. So that's A written as I, J and K because we're dealing with mechanics. So 10I minus 2J minus 6K. So that will be the acceleration in meters per second, nice and easy. The magnitude acceleration, so we're just going to do Pythagoras on that. So we'll just do the length of that. So it's going to be the square root of 10 squared plus negative 2 squared plus negative 6 squared. So that's going to be 100 plus 4 plus 36, which is going to be the square root of 140. So something like that for part C. Could simplify it down if you need to. And then part D, the distance travelled by the particle in the first 6 seconds. Right, so this is where we're going to basically use Suvat. So SUVAT. Now, that's 5 because it's the distance traveled, 6, the distance travelled in the first 6 seconds. So that's the 6 there. The acceleration we can use the root 140 here. Okay, we're told that given a particle starts from rest, so u is 0, and we want to find the distant travel, so we don't care about v, we want to find s, so we want a formula that's got s, u, a in t in it, and now because we've actually worked these out as scalars, we don't need the vectors anymore. So s equals ut plus half at squared, so s equals 0 times 6 plus half times root 140 times by 6 squared. Here we go. And we'll get s equals, let's work it out because it's 36 root 35. Seems a bit strange. Maybe that's right. Okay, so that's 0. And then I've got 0.5 times by square root 140 times by 36. Oh yeah, it is 36 root 35. 3 significant figures, 2, 1, 3, 213 meters to 3 significant figures.